Today we're going to have a look at what is WDM. WDM is the abbreviation for wavelength division multiplexing. It was first introduced in 1995. And when it was first introduced, WDM was only able to transmit 4 2.5 gigabits per second channels. However, the number of channels increased rapidly to 16, then to 32. This is due to the frequency spacing being reduced down to 100 GHz, which is 0.8 nanometers. WDM combines multiple signals on laser beams at various wavelengths for transmission along fiber optic media. Each multiplex channel is demultiplexed into the original signal at the destination by wavelength sensitive filters and a demultiplexer. The single mode operation for WDM is 1310 to 1550 nanometers, whereas the multimode operation is from 850 to 1310 nanometer. Initially, WDM was employed as a point-to-point technology, but has since evolved to star, bus, and ring networks, including arbitrary connected mesh networks utilizing intelligent network elements such as reconfigurable optical cross-connects or reconfigurable optical add-drop multiplexer, or commonly known as ROADMS. The supported applications are as shown in the pictures, which is plain old telephone service, internet data, business to business services. The advantages of WDM are as follows. It has greater transmission capacity. It also provides duplex transmission, and it also supports the simultaneous transmission of various signals. WDM is also easily expandable and costs much lower than replacing or adding on new fiber optic cables. WDM also provides faster access to new channels. Now we'll have a look at how to increase the data rate of WDM. One of the ways that we can increase the data rate of WDM is by dense wavelength division multiplexing. Using this technique, we are able to increase or multiplex up to 80 channels over one pair of fiber. As we can see, WDM has evolved from point-to-point optical transport to fixed multi-point network. So this is easy to implement. Next, we are going to look at the components of a DWDM system. The first is the terminal multiplexer, which contains a wavelength converting transponder for each data signal, an optical multiplexer, and where necessary, an optical amplifier. The next one is the intermediate line repeater, which is placed every 80 to 100 km to compensate for the loss of optical power as the signal travels along the fiber. An intermediate optical terminal is a site that amplifies the multi-wavelength signal that may have traversed up to 140 km or more before reaching the remote site. A terminal demultiplexer consists of an optical demultiplexer and one or more wavelength converting transponders, which separates the multi-wavelength optical signal back into individual data signal and outputs them on separate fibers for client layer systems. The technology that allows this high-speed, high-volume transmission is in the optical amplifier. We shall have a look at several types of optical amplifiers. The first is a semiconductor optical amplifier. The second will be a distributed fiber amplifier, which is doped in erbium, and also Raman amplifiers. So for semiconductor amplifier, it is similar to laser diodes, but emission is triggered by input optical signal. The advantages of semiconductor optical amplifiers are that they are able to work in any wavelength, they have high integration, are compact, and have low power consumption. However, gain fluctuation with signal bit rate is one of its disadvantages. There is also crosstalk that occurs between wavelengths. There are two types of semiconductor optical amplifiers which are currently widely in use in the market right now, which is the Fabry-Perot amplifier and the traveling wave amplifier. The next type of optical amplifier that we'll have a look at is the distributed fiber amplifier, or the EDFA. The reason why it is called the EDFA is because this amplifier is usually doped with the rare neural erbium, hence the name EDFA. It has a long fiber length of up to 10 to 30 meters. The advantages of the EDFA are that it has low coupling loss, it is transparent signal format, and bitrate makes it easy to handle. It also has no crosstalk and operates on a broad spectrum of 1530 to 1560 nanometers. However, the disadvantage of this amplifier is that it only works in specific wavelengths. The last type of amplifier that we'll have a look at is Raman amplifiers. Raman amplifiers work very well in variable wavelength amplification. They are very compatible with installed SM fiber. They can also be used to extend the range of EDFAs. Raman amplifiers have low average power and reduced crosstalk. However, due to the high output capacity of Raman amplifiers, they also require high pump power requirements. They also require sophisticated gain control for smooth channel control. So we have come to the last part of our presentation, which is the conclusion. And in conclusion, I would like to say that DWDM provides almost endless capacity expansion, as it allows service providers to expand capacity in any portion of their networks so they can address congestion due to high capacity demands. DWDM systems also reduce the need for multiple amplifiers, which result in fewer interruptions and improve efficiency. Aside from being able to integrate diverse technologies into one physical infrastructure, DWDM is bitrate and format independent, and thus allows for ATM, SONET, and IP networks to be multiplexed seamlessly and without the need of conversion. Well-engineered DWDM systems offer component reliability, system availability, and system margin. And there is also the fact that DWDM systems are very scalable, and it allows for integration of OC48 and mature OC192 systems, which can expand capacity and data rates of up to 40 Gbps and beyond. Thank you.